metaprogramming. Let me give you a non-frivolous example of metaprogramming, and that's client-side rendering. I'm a mere theoretician, so I know nothing about the internet, but my students tell me that in 2017, all trendy web services are using client-side rendering, and that works as follows. You write your web service in some framework like Flask, you pipe the program through a processor like Ginia, you get a program, for example in Python, which you put on your server. Every time someone requests a page, that program generates a little page that has some HTML, some CSS, and JavaScript. That is then sent to the browser where this program is rendered. Sorry, this web page is rendered, but it's not really a web page. All we want to do is run this JavaScript. The JavaScript then maybe probes what kind of display do we have, and it then generates on the client, using the client's resources, the actual web page that we're interested in, which probably also has JavaScript, which then talks to the DOM and stuff like that. I don't need to say anything about the difficulties from a software engineering point of view of this setup about verification. What I would like to draw your attention to is what is going on here. We have a program generated by a meta-program, which is generated by a meta-meta-program, which is generated by a meta-meta-meta-program. Okay? So this stuff is really being used in industry. There's your relevance. What is most fascinating, I find, is even though we have wildly different languages here, what they do from a meta-programming point of view is basically always the same. And that is what we like to exhibit in a very clear-cut way. So the research hypothesis that we had when we started writing this paper is the reason, the 5%, the gap in verification of metaprogramming is because there is no real unifying, very simple, very foundational way of looking at metaprogramming that exhibits all the key phenomena that I shall enumerate in a minute as first-class citizens. That really prevents theoreticians from thinking about program logics and stuff like that. And the purpose of this paper is to change this. If I want to be very glib, this is what the paper tries to solve. In order to be foundational, we must strip away almost everything. We need to boil down to the essences. And that means we must basically ignore everything that has been the focus of metaprogramming research so far. We don't care for now about non-homogeneous. We completely ignore hygiene. There's no agreement on what hygiene should be. There's even less agreement on what types should be for metaprogramming. We ignore it. We don't care about equality. We don't care about what the syntax looks like. Performance, who cares? And we ignore some edge cases of metaprogramming, for example, string rewriting that you have in the C preprocessing. Our hope is, of course, that later, once you have a nice simple calculus, you can think about those in a principled way. This was a very negative description. Let's be positive. And here's our second research hypothesis, namely that the very essence of metaprogramming, that which should be exposed in extreme clarity, are the following points. Of course, we need code as data. We do homogeneous only. That's Occam's razor. Almost any problem with metaprogramming already occurs in homogeneous, so there's no need of worrying about heterogeneous. Then we have language levels. We've seen in the client-side rendering that we need several. There's no need to stop at any particular level, just like with functional programming. You have arbitrary high-order functions. Levels are only interesting if we can navigate up and down, so there needs to be a consistent way of navigation. And then finally, a subtle point that is not always brought forward with the required clarity, I think, is that the computation in such a foundation should only come from the base language. So there's nothing higher up that is a form of computation that isn't driven by what's going on in the base. I'll come back to that later. Before I give you the formalism, because we're trying to describe the empirical reality of what people do with metaprogramming, let's survey very briefly the design space following these three questions. What kind of metaprogramming are we doing? When is it executed? And how, and this is the most important point, are programs represented as data? I already mentioned homogeneous versus heterogeneous. These are edge cases. If you have strings, of course, you can always do heterogeneous. And I think C++ templates really kind of intermediate, but I think they're heterogeneous. We restrict ourselves to homogeneous, as I already said. There's a different orthogonal distinction between generative and intentional. Generative means producing a program as data. Intentional means consuming. There's some duality going on, which I can't really quite pin down formally. Anyway, applying Occam's razor again, we think that generative already contains most of the interesting problems. So we restrict ourselves to generative. And now we come to the choice of representation. And if you look at all the mainstream languages, there's essentially three choices. Strings, there's the bedrock of compilers, abstract syntax trees. There's nothing I need to tell a programming language audience about ASTs. Probably everybody of you has written at least 10 compilers. And then there's quasi-quotes, where programs in a sense are represented by themselves, using some kind of marker to distinguish programs as data from programs. The marker can be quotation marks, the marker can be funny quotes, or the Scala community uses types. That's also very interesting. For those of you who haven't come across quasi-quotes, a quote, here's an example of a quote, and a quasi-quote is really a quote where part of the content of the quote is being computed. And the places where the computation happens, they are demarcated by some funny brackets. When you evaluate such a language, I recommend 3 evaluation criteria. What is the syntactic overhead of using that specific data structure? What is the support for generating only valid programs? And what is the expressivity of the formalism? Valid here is a bit vague. There are many different notions of validity. In 2017, this basically means syntactically valid. Of course, we can dream and think about only generating type-correct programs, but it's basically not a completely solved problem. And expressivity is, are there restrictions on the kind of metaprogramming you can do? Here's a little bit of taxonomy. Strings are super terse because programs are represented by themselves, and they're as expressive as we can hope. But for reasons I mentioned at the beginning, they are terrible if we're interested in correctness. So we ignore them. Abstract syntax trees help us with validity, and you can also do anything with them. So we want to look at them as well. They have a major problem, which is that they're really verbose. And there's a reason why every compiler you've ever used has a front end, has a lexer, has a parser, because as a human, you really don't want to write the ASTs for large programs. And the reason why most approaches also provide quasi-quotes is precisely this. We want to have a mechanism that lets us avoid writing ASTs by hand. The problem with quasi-quotes is that they are not as expressive as the other 2 choices. There are forms of metaprogramming that you cannot express here. And that's why we really want to have both of those, ASTs and quasi-quotes in our model. And we want to give both of them first-class status and make it very clear how they relate. There's another dimension, which is compile time versus runtime metaprogramming. And they're very similar, but they're subtly different, and it's about when and how often the effects happen. At compile time, the effect happens once during compilation, and then every time you run the executable, the effect is in some sense frozen in the executable, whereas runtime metaprogramming means you regenerate the effect on every run, and that also means the effect can change over time. Once again, it's important to give both first-class status, because both are important and both are heavily used. And of course, we're interested in how they relate. Okay, let's be formal. Let's do this for the Lambda calculus. We're untyped, and we use call by value, but that's a contingent choice. Here's the syntax. And all we do is, for each syntactic construct, we add an AST. You have all done this before, so there's nothing clever. So what we do in essence here is we take a copy of the language, and we say one copy is the programs, the other copy is programs as data. And there's nothing Lambda Calculus specific here. Let's now start with adding compile-time metaprogramming. What we need to be able to do is compute parts of the program at compile time. So we need markers that say, okay, here is the part that you need to compute during compilation. And we add this piece of syntax, which we call a down-ML, and the down should remind you of going down a meta level. We will later also go up a meta level, but that comes later. The meaning of this is really straightforward. The M in here is a program that computes part of the program under computation. So this M must be evaluated, so run at compile time. The evaluation yields as a value an AST, hopefully, otherwise the program is stuck. And the AST, program as data, is then converted into a program which is spliced into the hole that is denoted by the marker. And then the compilation proceeds. Once all these guys are disappeared, we have a normal compilation process. And in order to model this, we turn Lambda Calculus into a two-phase form of computation. The runtime computation is just the normal Lambda Calculus reduction relation, beta reduction or call by value, whatever you like. And then we put another compile time relation in front of this. The compile time relation is really simple. All it essentially does, and this is what the black rules do, is we search for these down MLs. And when we find one of them, we recursively, because we also allow meta, and meta, we recursively remove down MLs in this M. We get a program. We run this program using call by value or whatever our reduction relation is. We get an AST, program as data, which we turn into a program that's the result. So DL stands for down a level, which essentially peels off one layer of meta. Here's how this relation works. We essentially get rid of one layer of AST. So if we have an AST 17, this turns into 17. By the way, in this setting, once we go up a level, variables become strings. We don't alpha convert strings, and that leads to all manner of funny capturing, and it should, because that is part of the key problems of dealing with metaprogramming. Okay, that was compile time. Now let's do the same for runtime. All we need to add is a mechanism of running an AST code as data at runtime. And we add an eval mechanism. But because we also want future stages, we want to be able to construct future stages that eventually eval something, we also need an AST that corresponds to eval. And that's the only change syntactically. And semantically, essentially, we add the obvious rule for eval. We evaluate, run the argument until it's a value. This must be a program as data, so an AST. We go down a level, so we de-ASTify, getting a program n, and we then run that n using lambda reduction to completion, and that's the result. So completely trivial, basically. We also need to deal with higher order metaprogramming, so we need to be able to represent ASTs that represent ASTs. That can easily be done, but I won't talk about it because I don't really have that much time. Okay, so if we stop here, we have a runtime and compile time metaprogramming version of the Lambda Calculus, but it only uses ASTs as representation. We really want quasi-quotes as well. Adding them syntactically is trivial. This is our representation of the quoting mechanism, and the up arrow should remind you that we're now going up a meta level. The interesting question is, how do these two forms of representation relate? And our choice, which is the choice that is implicit in all compilers, basically, but it's not usually remarked upon. Our choice is that quasi-quotes are simply syntactic sugar for the corresponding ASTs. So if we quote the program 2, this is just a convenient shorthand for the AST representing 2. But the trick is, when do we do the conversion? We do the conversion at compile time. And you can think of the conversion as a form of compile time metaprogramming itself. So if you only have runtime metaprogramming with quasi-quotes, you still do compile time metaprogramming under the hood. There's one more thing missing, which is the holes inside quasi-quotes. we must model them. They are the place where the quotation is, where parts of the computation is computed. And how do we do this? Well, we already have a marker. We use it to denote where compile time computation happen. It's the down arrow. We go down a meta level, and we simply reuse it. So if we have one of those down arrow guys inside a quote, this means this part here is evaluated first and is then spliced into the rest of this quote. So if we quote 2 plus 7, that stands for this AST. But if we quote 2 plus, and then the 7 bit is computed, we get the same AST. The corresponding operation semantics is here. It's quite straightforward, but you need a little bit of time to digest it. The important bit is that we intertwine the quotation mechanism with the compile time evaluation mechanism. And this gives us, in some sense, a very tight relationship between both quasi-quotes and ASTs and compile time and runtime metaprogramming. So the up is really the quotation mechanism, and the down is the whole formation mechanism. And that, ladies and gentlemen, concludes the formal bit. If you think that was trivia, we have succeeded. Now comes the most interesting part of the talk, because nothing in the development had anything to do with the Lambda Calculus. The Lambda Calculus was treated as a black box. It was a completely generic process. If we had instead used an arbitrary language L, we would have simply created the representation by copying the language, add the eval thing, add up and down, and that's the extended syntax. There's nothing Lambda Calculus specific. And even more interesting is the operational semantics, because we treated the operational semantics of Lambda Calculus also as a black box. We didn't remove any Lambda Calculus rules. We didn't even make any decision in our new operational semantics contingent upon what Lambda does. We treated it really as a black box. And this is, I think, formalizes this idea that the computation is driven by the base language. Quite why this is so important, I would like, in the spirit of Socratic teaching, I would like to leave as a provocation to you.
Thanks, cool stuff. In the end, do you really need an AST?
That depends on the meaning of need. There's, for example, the meta tradition, which on surface syntax doesn't have ASTs. It just has quasi-quotes, and that works for many situations. In fact, if you can get away with only using quasi-quotes, it's very convenient. Under the hood, of course, the compiler uses ASTs. That's one meaning of need. But there is really forms of metaprogramming that you cannot do with ASTs only. Let me give you an example. Sorry, with quasi-quotes only. You'd want a function that takes two numbers, n and I, and it should return the ith projection function, lambda x. So this is not really, you can't really do it, as far as I can tell, with quasi-quotes. And that's why you need something more expressive. So in that sense, I think you do need it. And empirically, many languages do provide it, and we felt we wanted to explain how the two relate.
So you claim that at least the formalization should have it?
Yes.
Sorry.
You have been talking about generative and intentional metaprogramming.
Yeah.
And I think that your calculus supports both. Am I right?
No, so what we haven't given explicitly is some form of pattern matching, a consumer of quasi-quotes. Of course, if you have ASTs, they're just algebraic data types, and then if your base language has a way of analyzing them, you have it. But languages like, for example, the Intel language Reflect, they have a pattern matching for code which we haven't explicitly provided, but I think it would be straightforward, especially in an untyped language, to add it.
But even if you haven't got pattern matching nor code, you could define functions that run on code and give you results, and then you compare.
Yeah, no,
so you can do both in your calculus.
Yes.
All right, thank you.
Thanks.
Let's thank again our speaker, and then we'll hear a little bit from Simon.